Okay, in this video, we're going to give an overview of the simplex method. So we saw an example of it and sort of worked through it. Now let's talk about it from a bird's eye view and sort of discuss the steps along the way. So first step is set up, put your system into the Tableau format, which means that we're sort of going to arrange columns for Z, each of our original variables, which I'm kind of writing an X vector here to kind of say all of those X variables, all your slack variables, and your right-hand side. And so columns for each of them. And sort of if this is sort of our setup for our maximization LP in augmented form, then this is what that Tableau is going to look like. Okay. Initially, we're going to, like, our constraint matrix is going to show up down here. We're going to have an identity matrix. We're going to have our right-hand side. And then this line here is essentially our objective row, which is going to have a 1 for Z. All of our coefficients of our X of that objective function are going to get negatives when we move them over to the left side of the equation. And then slack variables don't show up in our objective row. And so they're all going to have zeros in the objective row. So that's the setup, and we'll see that a couple times. Next step is to choose an initial set of basic variables that give a basic feasible solution. Okay. In practice, this is difficult, but to begin with, we'll say that we want to choose just the slack variables as basic variables. Okay. And at least for these first few problems that we do, that will work every time. And it will sort of start us off at 0, 0, 0 in the original variables. And as long as that 0, 0, 0 is a feasible solution, that's a good place to start. Okay. Next step is we test for optimality. We look at the objective row, and if any of the entries are negative, we can bring that variable into the basis. Okay. I use the kind of rule of thumb of choosing the most negative because that will sort of lead to the fastest improvement. But there's other heuristics that are used in practice. That's just the simplest one to remember. So any negative variable would work. You choose whichever one you want. If all the entries in that objective row are positive for a maximization, or I should say, if you're doing minimization, the signs get flipped here. If all of them are positive, then we've reached the optimal value. We're at a stopping point. We're good to go. If all of them are non-negative and we got some non-basic variables that have 0 objective value, then there might actually be, or there will be, multiple equivalent optimal solutions. Okay, and so sometimes we get a tie where multiple corner points have the same objective value, and then actually the entire edge between them actually also has the same objective value. That happens. There might be multiple optimal values. Okay, and if we wanted to, we could do another iteration with that 0 cost column as the entering variable to find the other optimal solutions. Okay, once we check for optimality, choose an entering variable in the same step, then we need to choose an exit variable. And to do that, we use a ratio test where we take the right-hand side divided by the values in our entering variable column. Okay, if the entering variable column has zeros or negatives, ignore those rows, but otherwise take right-hand side divided by entering variable column. Okay, we want to choose the smallest ratio that's positive as our exiting variable, as our pivot row. Yeah, if the smallest ratio is 0, then you're at a degenerate solution where sort of multiple or some of the basic variables were 0. Then choose that and use that row as the exiting variable. If all the pivot column values are negative or 0, then you've actually got an unbounded solution in that direction, and you've got a objective that's unbounded, which means that you're moving in a direction that has improvement for your problem, and you can keep moving in that direction off to infinity. And so usually this means that your problem was ill-posed in some way and that you were maybe missing a constraint when you formulated or set up the problem. Okay. Or sometimes it, yeah, just says that you can make your objective arbitrarily large, which sounds nice. Usually there's some actual limiting in practice. Next step is we pivot on our entering variable column and exiting variable row. So we circle that row, that column. We want to turn that entering variable column into a standard basis vector with 1 in the exiting variable row and 0 everywhere else. Okay, use elementary row operations to do that, using that exiting row, that pivot row as your sort of tool, and adding or subtracting multiples of it to other rows. Then we get into a loop. And so we repeat steps 3 through 5 in a loop. Okay, we loop through steps 3 to 5 until finally, when we come back to step 3, we test for optimality and find that we've reached optimality. Okay, so this was an overview video, the Simplex method. I encourage you to take a while to read through this handout and kind of understand what all is going on. But that's the overview. I'll stop this video, and in the next video, we'll go through another example.